Picture the darkest corner of the universe, where not even light can escape. A silent, invisible giant that swallows stars and warps the very fabric of reality around it. For decades, black holes have been the ultimate cosmic mystery. Objects so strange they defy common sense and challenge everything we think we understand about space, time, and existence itself. But what if the most fascinating truths about black holes haven't even been discovered yet? What if many of our long-held assumptions are incomplete, or maybe even entirely wrong? Today, we're setting off on a journey into the unknown, exploring 25 incredible theories about black holes that just might be true. Some sound like they're pulled straight from science fiction gateways to other universes, tunnels through space-time, or even cosmic engines birthing new realities. Others propose that black holes might not be entirely black after all, leaking mysterious radiation or holding onto fragments of what they've devoured. What's most exciting is that many of these ideas aren't just wild guesses, they're grounded in real science, supported by brilliant minds and cutting-edge research that's reshaping our understanding of the cosmos. So whether you're new to the wonders of space or a seasoned enthusiast of its deepest secrets, you're in for a ride. We'll traverse concepts that bend the mind and challenge the imagination, all while keeping things as clear and engaging as possible. There's no need for a PhD in astrophysics here, just curiosity and a sense of wonder. By the end of our exploration, you may never look at the night sky the same way again. The universe is stranger and more magnificent than we ever thought, and it's time to dive in. Our journey begins with one of the most captivating ideas ever proposed about these cosmic enigmas: the possibility that a black hole is not an end, but a beginning. Imagine plunging into the darkness not to be crushed into oblivion, but to be hurled across the cosmos, emerging moments later in a distant galaxy, or perhaps in a universe entirely separate from our own. This is the incredible promise of the black hole wormhole theory. At its heart, this idea is rooted in the work of Albert Einstein himself. Together with his colleague Nathan Rosen, Einstein's equations of general relativity revealed that the extreme warping of spacetime at the center of a black hole could, in theory, connect to another such distortion, forming a bridge. This concept, now famously known as an Einstein-Rosen bridge, suggests the singularity might not be a point of infinite density, but a gateway, a tunnel through the very fabric of spacetime. For this to be more than a mathematical curiosity and a potential shortcut for interstellar travel, the wormhole would need to be traversable. This is where the theory faces its greatest hurdles. Based on our current understanding, such a bridge would be incredibly unstable. The moment any matter, or even a single particle of light, tried to pass through, the tunnel would likely collapse instantaneously, severing the connection. The gravitational forces involved are so extreme that anything entering would be subjected to a process physicists call spaghettification, stretched into a long, thin stream of atoms, a journey that seems decidedly one-way and final. Yet, what if new physics could provide a solution? Some theoretical models suggest that exotic forms of matter with negative energy or negative mass could be used to prop the wormhole open, effectively lining the tunnel to prevent its collapse. This speculative material would have repulsive gravitational properties, acting against the crushing weight of the singularity to keep the passageway stable and open for travel. While we have no confirmed examples of such exotic matter, its potential existence is not outright forbidden by the laws of physics, leaving the door tantalizingly ajar for this extraordinary possibility. This transforms the black hole from a mere cosmic vacuum cleaner into a potential stargate, a natural portal for unimaginable journeys. It provides a compelling, scientifically grounded answer to the question of what truly lies within the event horizon. We are no longer just staring into a pit of nothingness, but contemplating a doorway, one that could rewrite the rules of exploration and connect realities we once believed were forever separate. But if the first theory offered us a door, the next one gives that door an expiration date. It comes from one of the most brilliant minds in modern science, Stephen Hawking, and it completely upended our understanding of black holes as eternal prisons. Hawking proposed that these cosmic giants are not completely black after all. They actually emit radiation and can slowly evaporate, fading out of existence over unimaginable eons. This revolutionary idea, now known as Hawking radiation, forces us to look at the very edge of a black hole, the event horizon, through the bizarre lens of quantum mechanics. In the seemingly empty vacuum of space, pairs of virtual particles are constantly flickering in and out of existence. These are particles and their antiparticle counterparts, borrowing energy from the universe for a split second before they typically collide and annihilate each other, paying the energy debt back. The magic happens when this particle pair pops into existence right at the precipice of the event horizon. In a fantastically unlikely but statistically inevitable event, one particle might get tugged by the black hole's immense gravity and fall across the point of no return, while its partner gets a reprieve and escapes into space. From the perspective of an outside observer, the black hole has just emitted a particle. To maintain energy conservation, the particle that fell in must have had negative energy, which effectively reduces the overall mass, and thus the gravitational pull of the black hole itself. This process is incredibly slow for a typical black hole. One with the mass of our Sun would take longer than the current age of the universe to evaporate in any significant way. But for smaller, hypothetical black holes, the story is very different. A black hole with the mass of a small asteroid would be radiating away energy at a tremendous rate, glowing with intense heat, and ultimately ending its life not with a whisper, but with a bang, a final, spectacular burst of high-energy radiation equivalent to 1,000,001 megaton hydrogen bombs detonating at once. Hawking's theory creates a fascinating paradox, a deep conflict between the laws of gravity and quantum mechanics. If a black hole evaporates, what happens to all the information about the matter it swallowed? Quantum physics states that information cannot be destroyed, yet general relativity suggests it is lost forever behind the event horizon. This black hole information paradox remains one of the most heated debates in theoretical physics, a puzzle that hints at a deeper, more complete theory of quantum gravity waiting to be discovered. Hawking radiation doesn't just mean black holes die. It means they might take our current understanding of the universe with them. If black holes represent the universe's ultimate one-way street, a point of no return where everything goes in and nothing comes out, then what would the exact opposite look like? Enter the white hole, a hypothetical cosmic geyser that violently expels matter and energy into the universe while completely refusing to let anything back in. It's the mathematical mirror image of a black hole, born from the very same equations of general relativity that predicted its dark twin. The concept emerges when scientists play with Einstein's field equations and run the cosmic film reel in reverse. If a black hole's gravity is so powerful that it traps everything inside an event horizon, then a white hole would have a gravity so repulsive that it pushes everything away, creating an event horizon that is utterly impenetrable from the outside. Nothing, not matter, not light, not even a single photon, could cross its boundary. It wouldn't be a destination, it would be a source, a fountain of energy and particles constantly erupting into the cosmos. One of the most intriguing possibilities is that a white hole could be the other end of a black hole wormhole. The matter and energy swallowed by a black hole in our universe might not be destroyed at a singularity, but instead could be traveling through an Einstein-Rosen bridge, only to be violently ejected out of a white hole in another time or another universe entirely. This offers a potential solution to the information paradox, suggesting that what a black hole consumes isn't lost, but merely relocated. Perhaps the most grand and captivating hypothesis is that our entire universe, the Big Bang itself, could have been the explosive outburst of a white hole in a larger, parent cosmos. This would mean our cosmic genesis wasn't a singular event from a point of infinite density, but rather the result of a white hole erupting from a different region of space-time. In this view, the universe wasn't born from nothing but from something. A white hole spewing out the raw material for everything we see today. So if these objects are mathematically possible and conceptually so powerful, why have we never seen one? The prevailing theory is that white holes are profoundly unstable, or perhaps even impossible to form through any known natural process. While the math allows for them as a solution, nature might forbid them. A white hole would be bursting with immense energy, and any interaction with even the faintest trace of external matter, a single dust particle or hydrogen atom, could cause its delicate structure to collapse, potentially triggering a transformation back into a black hole. Their existence might be fleeting, lasting only for a fraction of a second before they break down, which would make them incredibly difficult, if not impossible, to detect across the vast distances of space. This leaves the white hole in a fascinating limbo. It remains a brilliant thought experiment, a tool that challenges our understanding of physics and forces us to ask deeper questions about the nature of time, causality, and the very origins of our universe. It shows us that for every cosmic rule, there might be an exception waiting in the equations, a strange and wonderful possibility that the universe still has secrets to reveal. While the concepts of wormholes and white holes stretch the imagination, another theory brings the mystery of black holes closer to one of the greatest unsolved problems in all of physics, the nature of dark matter. We know this invisible, mysterious substance exists because of its gravitational pull on galaxies, but we have never directly observed it or determined what it's made of. What if the answer isn't a cloud of exotic particles, but trillions upon trillions of ancient black holes scattered throughout the cosmos? This idea hinges on a specific type of object known as a primordial black hole. Unlike the stellar black holes formed from the collapse of massive stars, these would be relics from the universe's explosive infancy. In the first fleeting moments after the Big Bang, the cosmos was not perfectly smooth. Pockets of space existed with incredibly dense concentrations of matter. If one of these regions was dense enough, it could have collapsed under its own weight, directly forming a black hole without ever needing a star. The mass of these objects wouldn't be limited to a few times that of our Sun. They could be almost anything, from the weight of a small asteroid to many times the mass of the one at our galaxy's center. For primordial black holes to be the dark matter we've been searching for, the majority would likely exist within a specific mass range. If they were too small, say around the mass of a mountain, they would have evaporated by now due to Hawking radiation, ending their lives in a flash of gamma rays we likely would have detected. If they were too large, their gravitational influence would be too obvious, disrupting the delicate dance of star clusters and the structure of galaxies in ways we don't observe. The sweet spot might be black holes with masses similar to a large planet or even a small star. Objects that are massive enough to be stable yet small enough to remain effectively invisible. This is how they would evade detection. A solitary black hole of this size, drifting in the emptiness between stars, would be nearly impossible to see. It wouldn't be actively feeding on gas and dust, so it wouldn't be surrounded by a glowing accretion disk. It would simply be a cold, dark knot of gravity, betraying its presence only through the subtle way it bends the fabric of spacetime around it. A vast population of these hidden objects could form a massive, unseen gravitational scaffold that holds galaxies together and explains the rotation curves that first hinted at dark matter's existence. So how do we search for something that is, by its very nature, designed to hide? Astronomers have devised clever methods to catch these ghosts. One of the most promising is gravitational microlensing. If a primordial black hole passes directly between Earth and a distant star, its gravity will act like a lens, bending and focusing the star's light. From our perspective, the star would temporarily appear to brighten, then fade as the black hole moves on. By monitoring millions of stars for these characteristic flashes, projects like the optical gravitational lensing experiment have placed serious constraints on how many of these objects could be lurking in the halo of our galaxy. Other searches look for different signatures. Some models suggest that when these small black holes occasionally pass through a dense cloud of gas, they might generate a faint, specific radio signal as they subtly heat the material. Others propose that a primordial black hole interacting with a neutron star could capture it, causing the star to emit gravitational waves that observatories like LIGO could potentially detect. While no definitive proof has been found yet, the search continues, and each passing year rules out more possibilities, bringing us closer to either confirming this theory or finally putting it to rest. The notion that the elusive dark matter holding our universe together might be a sea of ancient black holes remains one of the most compelling and elegant ideas in modern cosmology. But if we accept that black holes can slowly fade away through Hawking radiation, we're immediately confronted with one of the most profound puzzles in all of physics. What happens to all the stuff that fell in? Quantum mechanics, the rulebook for the very small, states with absolute certainty that information cannot be destroyed. Every particle that enters a black hole carries with it a specific set of information: its mass, its charge, its spin. According to quantum law, that information must be preserved, even if the particle itself is seemingly gone forever. Yet, general relativity, which governs the immense gravity of black holes, paints a very different picture. It suggests that once anything crosses the event horizon, all of that information is irretrievably lost, shredded and crushed into the singularity. This is the infamous black hole information paradox, a direct contradiction between our two most successful theories of the universe. One of the most radical and fascinating solutions to this paradox comes not from rethinking black holes, but from rethinking the very nature of reality. This is the holographic principle, an idea born from the mathematics of string theory. It proposes a possibility so strange it sounds like science fiction, that all the information about a three-dimensional volume of space, including everything that happens within it, can be entirely encoded on a two-dimensional surface that surrounds it, much like a hologram. To understand this, think of an ordinary credit card hologram. The flat, shiny surface contains all the information needed to project a three-dimensional image that seems to float in space. The holographic principle applies this same concept to the universe itself, but on a cosmic scale. In the context of a black hole, it suggests that every single bit of information about every star, planet, or particle that has ever fallen in is not lost inside. Instead, it is perfectly preserved, pixel by pixel, on the two-dimensional surface of the event horizon. The event horizon acts as a vast, cosmic hard drive, storing a complete description of the black hole's contents on its boundary. This idea elegantly resolves the information paradox. When Hawking radiation causes a black hole to evaporate, it doesn't destroy the information. That information was never truly inside the black hole to begin with. It was always encoded on the surface. As the black hole radiates and shrinks, that information is slowly and carefully released back into the universe, embedded within the radiation itself. The paradox vanishes because information is conserved, just as quantum mechanics demands. The implications of this principle stretch far beyond black holes and ripple through our entire understanding of reality. If the information for a three-dimensional black hole can be stored on a two-dimensional surface, perhaps our entire three-dimensional universe is also just a projection. The world we see and feel, the depth of space, the solidity of matter, might be a holographic illusion emerging from a vast, complex code written on a distant, two-dimensional surface at the very edge of the cosmos. This isn't just a quirky analogy. It's a serious theoretical framework that some physicists believe could be the key to unifying gravity with quantum mechanics. finally creating a complete theory of quantum gravity. It suggests that the fundamental building blocks of reality might not be particles or strings in space, but bits of information, a cosmic code from which spacetime itself is generated. Building on the idea that black holes can radiate energy, we arrive at one of the most ambitious and far-sighted theories in all of cosmology, the concept of a black hole starship. Imagine not just observing these cosmic engines from a distance, but capturing one, taming its incredible power, and using it as the heart of a vessel capable of crossing the interstellar void. This isn't just science fiction, it's a theoretical possibility grounded in the physics of Hawking radiation. The entire concept hinges on the relationship between a black hole's size and its temperature. As Hawking discovered, the smaller a black hole is, the hotter it burns. A black hole with the mass of a mountain would radiate energy at a tremendous rate, glowing with the intensity of a powerful engine. For interstellar travel, the ideal power source would be a micro black hole, one with a mass roughly equal to a few million metric tons. An object this dense would be smaller than a single proton, yet its event horizon would emit Hawking radiation at a temperature of billions of degrees, converting matter into energy with near-perfect efficiency. The engineering behind such a vessel is almost beyond comprehension. First, you would need to create or capture a suitable micro-black hole. One proposed method involves using an immense laser array to focus energy into a volume of space so small that it collapses into a black hole. Once created, this infinitesimally small yet incredibly massive object would have to be contained. It couldn't be held in any physical bottle. Instead, it would need to be suspended using powerful magnetic or gravitational fields, perfectly balanced at the center of a spherical chamber to prevent it from drifting and consuming the ship itself. The propulsion system would then work by carefully feeding this captive singularity. A stream of matter, perhaps hydrogen collected from the interstellar medium by a vast magnetic scoop, would be directed into the chamber. As this matter crosses the event horizon, the black hole would convert it directly into Hawking radiation, a blazing torrent of high-energy photons and particles. This radiation would then be directed out of a nozzle by immense mirrors, creating thrust. The beauty of this system is its efficiency. It would be converting mass to energy with a yield approaching that of matter-antimatter annihilation, the most potent reaction known to physics. The performance of such an engine would be staggering. Calculations suggest a black hole starship could sustain acceleration for years, potentially reaching a significant fraction of the speed of light. A journey to a nearby star system, which would take tens of thousands of years with current technology, could be reduced to a matter of decades. This wouldn't just be a ship. It would be a moving world, a generation vessel powered by a miniature sun it carries within itself. Of course, the challenges are as monumental as the potential. The energy required to create the black hole in the first place is astronomical, containing an object that could evaporate in a flash of gamma rays if not perfectly managed presents an existential risk. And navigating with a weapon of planetary destruction at the core of your ship requires failsafes beyond our current imagination. Yet, for a civilization advanced enough to master such technology, the entire galaxy could become within reach, all thanks to harnessing the most destructive force in the universe and turning it into the ultimate engine of exploration. This leads us to one of the most speculative and mind-bending theories of all: the possibility that a black hole is not just an object, but a processor. What if the incomprehensible chaos within its event horizon is actually a form of computation? A natural quantum computer operating on a scale and at a speed we can scarcely conceive. This idea pushes the boundaries of physics and philosophy, suggesting that the universe might not just contain information, but that it might be thinking. To grasp this, we need to consider the ultimate fate of information that falls into a black hole. According to the holographic principle, every particle's worth of data, Every charge, spin, and mass is encoded onto the two-dimensional surface of the event horizon. This surface is not a smooth, featureless sphere. It's theorized to be made up of infinitesimally small, Planck-sized pixels, each one capable of holding a single bit of information. This transforms the event horizon into a vast, cosmic hard drive. But a hard drive is a storage device. A computer is something that processes that information. The question then becomes, does the black hole simply store this data, or does it also compute with it? The sheer density and energy at the singularity could provide the perfect environment for quantum computation on a grand scale. In our most advanced labs, quantum computers use qubits particles like electrons or photons that can be in multiple states at once, to perform calculations that would take classical computers millennia. Now imagine that process, but with the entire history of every star, planet, and cloud of gas that ever fell into the black hole. The singularity isn't just a point of infinite density. It could be a maelstrom where spacetime itself is being constantly rewritten, where the laws of physics are being recalculated in real time. This isn't computation as we designed it. It's computation as a fundamental property of the universe, an intrinsic function of extreme gravity. This speculative leap connects to an even more profound concept known as panpsychism, the idea that consciousness is a fundamental and ubiquitous feature of the universe, not just a product of complex biological brains. Some theorists propose that the sophisticated information processing occurring within a black hole could constitute a rudimentary form of cosmic consciousness. It wouldn't be consciousness as we experience it with thoughts and feelings, but a vast, alien form of awareness born from the complex interplay of matter, energy, and space-time. In this view, a black hole might not be a cold, dead end, but a moment of unified thought for the cosmos. The implications of this are staggering. It suggests that the universe might be self-aware in ways we cannot perceive, with black holes acting as nodal points in a vast cosmological network. Each one could be processing the information of its own devoured region of spacetime, and perhaps even communicating with others through the fabric of reality itself, via gravitational waves or something we haven't yet discovered. This transforms our picture of the cosmos from a collection of inert objects governed by blind forces into a potentially living, thinking entity. While this theory remains highly speculative and far from the scientific mainstream, it serves a crucial purpose. It challenges us to think about black holes not as destructive failures of physics, but as active participants in the universe's story. They become engines of transformation, not just of matter and energy, but of information itself. Whether they are literal quantum computers or not, the mere act of considering this possibility forces us to confront the deep, mysterious links between information, reality, and the very nature of existence. This astonishing concept turns our understanding of the cosmos inside out, proposing that the universe we inhabit, with its hundreds of billions of galaxies, might itself be the interior of an unimaginably vast black hole residing in a larger, parent universe. The theory doesn't just suggest a similarity. It proposes that a black hole's formation and our universe's birth could be one and the same event, offering a radical new perspective on the origin of everything. The foundation of this idea lies in the striking mathematical and physical parallels between the two most mysterious objects in cosmology: the Big Bang singularity and a black hole singularity. Both are points of infinite density where the known laws of physics break down. Both represent a boundary to spacetime itself. One is the beginning, and the other is typically seen as an end. But what if that distinction is just a matter of perspective? When we look at the equations describing the collapse of matter into a black hole and the expansion of the universe from a single point, they are eerily similar. This has led some physicists to speculate that the Big Bang wasn't a unique event from nothing, but was actually the formation of a black hole in a pre-existing, higher-dimensional universe. This perspective elegantly tackles one of cosmology's greatest puzzles, the initial conditions problem. Our universe appears to be perfectly fine-tuned for the existence of life. Its expansion rate, the strength of its fundamental forces, and the amount of matter and energy are all set with incredible precision. If any of these values were even slightly different, galaxies, stars, and planets could never have formed. From the inside of our universe, this seems like an inexplicable, miraculous coincidence. But if our universe was born from a black hole, this fine-tuning finds a potential explanation. The physical laws and constants we observe wouldn't be arbitrary. They would be an inheritance. They would be determined by the specific conditions of the collapse that formed the parent black hole, sculpted by the physics of that external, grander reality. In this model, what we perceive as the cosmic horizon, the maximum distance we can observe, about 46 billion light-years away, isn't just a limit based on the age and expansion of the universe. It could be our local event horizon. Just as nothing can escape from within a black hole, we cannot see beyond this cosmological boundary. The space outside our horizon isn't merely more empty space. It could be the interior of the parent universe, forever hidden from our view. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, might not be the echo of a creation event, but the Hawking radiation emitted by our universe's own event horizon, thermalized over billions of years. This leads to a captivating and almost fractal-like vision of reality. If our universe is a black hole in a larger cosmos, then it's possible that every black hole that forms within our own universe could itself contain an entire new cosmos, bubbling into existence with its own unique laws of physics. Our universe would not be the top level but merely one link in an infinite chain of nested realities. A cosmic matryoshka doll of universes within black holes within universes. Each new universe could have slightly different physical constants, creating a vast multiverse where only those with the right conditions for life, like ours, can give rise to observers who can ponder their own origins. While this theory provides a breathtakingly elegant framework, it is not without its significant challenges. The biggest hurdle is testability. How could we ever gather evidence for something that exists beyond our fundamental cosmic horizon? Any signal or information from the parent universe is, by the very definition of an event horizon, permanently inaccessible to us. Some researchers suggest that subtle imprints on the cosmic microwave background or specific patterns in the distribution of galaxies could hold clues, acting as a fingerprint from the collapse that created us. Others propose that the overall geometry of our universe might betray its origins. If we could determine that the universe is positively curved in a specific way, it might indicate we are living within a black hole. So far, our best measurements suggest the universe is flat, but the margins of error leave room for intriguing possibilities. Ultimately, this theory forces us to confront the limits of our knowledge and the true meaning of a singularity. It blurs the line between the beginning and the end, suggesting that a catastrophic collapse in one reality can be the glorious birth of another. It transforms the universe from a lonely, isolated existence into a potential family of cosmoses, each with its own history and fate, all connected through the most mysterious objects nature has ever conceived. If traversable wormholes offer a gateway across space, then a specific and extraordinary type might offer a journey through time itself. This brings us to one of the most tantalizing ideas in theoretical physics: the possibility that certain black holes could function as natural time machines. The key to this lies not with the simple black holes we've discussed so far, but with a more complex and dynamic variant: the rotating Kerr black hole, named after the mathematician Roy Kerr, who discovered the solution to Einstein's equations that describes it. A Kerr black hole isn't a static, singular point of infinite density. Instead, its immense rotation flings the singularity into the shape of a rapidly spinning ring. This ring singularity is fundamentally different. It isn't surrounded by a spherical event horizon from which there's no return. The intense centrifugal forces of the spin open up a completely new set of possibilities within the black hole's inner structure. Beyond the standard event horizon lies a second boundary called the ergosphere, and most importantly, a region known as the inner event horizon. Within this intricate architecture, the mathematics of general relativity reveals something astonishing: pathways known as closed time-like curves. A closed time-like curve is exactly what it sounds like: a path through the fabric of spacetime that loops back on itself. If you were to follow such a curve, you would inevitably return to the exact same point in both space and time from which you began. This isn't just a theoretical loop, it's a recipe for time travel. An object or person following this path could, in principle, journey into their own past. The ring singularity at the center of a Kerr black hole is theorized to be surrounded by a region filled with these curves, presenting a potential gateway to earlier moments in history. However, this incredible concept immediately confronts one of the most famous logical puzzles in science fiction: the grandfather paradox. Imagine traveling back in time, and whether by accident or design, preventing your own grandfather from meeting your grandmother. This would mean your parent was never born, and consequently, you would never have been born to travel back in time in the first place. It's a logical inconsistency that seems to make time travel an impossible fantasy, a violation of cause and effect that would unravel reality itself. Yet, physicists have proposed several compelling resolutions that keep the idea alive within the realm of quantum possibility. One solution is the idea of self-consistency, often associated with the physicist Igor Novikov. This principle suggests that the laws of physics would simply prevent any action that creates a paradox. You could travel to the past, but you would be physically incapable of changing it in any way that leads to a contradiction. Your actions would already be a part of established history, meaning you were always there. The timeline is fixed and immutable. Another, even stranger resolution comes from the many worlds interpretation of quantum mechanics. This theory posits that every possible outcome of every quantum event actually occurs, but in a vast, branching multiverse of parallel realities. In this view, a time traveler arriving in the past wouldn't be entering their own history, but rather branching off into a new, parallel universe that is nearly identical up to the moment of their arrival. Any action they take, even preventing a grandfather's meeting, would simply create a new timeline. The traveler's original universe remains unchanged, neatly sidestepping the paradox altogether. Even if the physics allows it, the engineering challenges of actually using a Kerr black hole for time travel are staggering beyond belief. First, you would have to reach a rotating black hole, which in itself is a journey of thousands of light years. Then, you would have to navigate past the event horizon and into the tortured spacetime near the ring singularity, without being torn apart by tidal forces or blasted by radiation. Most theoretical models suggest that the region containing closed time-like curves is likely unstable, potentially collapsing the moment any matter or energy tries to pass through it. To prevent this, you would need to line the tunnel with exotic matter possessing negative energy density, a substance we have no confirmed way of obtaining or containing. The energy required to create and stabilize such a passage would be on a scale that dwarfs the total output of stars across entire galaxies. So, while the equations of general relativity keep the door to time travel tantalizingly ajar, nature seems to have bolted it shut with layers of quantum mechanics and unimaginable physical requirements. The existence of closed time-like curves within Kerr black holes remains a brilliant mathematical curiosity, a testament to the strange and wonderful predictions of Einstein's theory. It shows us that time may not be the rigid, one-way street we perceive it to be. But even if it is flexible, the universe appears to have built-in safeguards that protect the sanctity of cause and effect, ensuring that history remains a story that can be read, but not rewritten. But if the idea of a black hole as a computer stretches the limits of our imagination, the next theory rewrites the rulebook entirely, proposing that the very foundation of a black hole might be something entirely different from the empty, dark void we imagine. This is the fuzzball theory, a radical idea born from string theory that suggests a black hole isn't a bottomless pit with a singularity at its core, but a giant, tangled ball of energy, a cosmic knot of the very fabric of spacetime itself. To understand this, we have to revisit the central problems it aims to solve: the information paradox and the dreaded firewall. The paradox, as we've discussed, is the conflict between quantum mechanics saying information can't be destroyed and general relativity suggesting it is inside a black hole. The firewall is a related and equally troubling idea. As physicists probed the information paradox, some calculations suggested that the event horizon, instead of being an unremarkable boundary you'd cross without noticing, might actually be a wall of blistering, high-energy radiation that would instantly incinerate anything falling in. This firewall seemed to be a necessary but absurd consequence of trying to preserve quantum information, and its existence would mean Einstein's principle of equivalence, which states that free falling through an event horizon should be an uneventful experience, was completely wrong. String theory, which proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings, offers a way out of this mess. The fuzzball theory emerges directly from this framework. It does away with the two most problematic features of the classic black hole: the empty interior and the point of infinite density. Instead, it proposes that a black hole is a giant, fuzzy ball of these fundamental strings. When a massive star collapses, it doesn't form a singularity. Instead, all the matter and energy that would have fallen in gets converted into a vast, convoluted ball of stringy energy that expands outward until it reaches the point where the event horizon was supposed to be. The surface of this fuzzball is the black hole. There is no empty space inside it and no sharp, point of no return boundary. This changes everything. There is no singularity where physics breaks down, because the entire interior is filled with a known, if exotic, form of matter. There is no information paradox because the information of every particle that formed the black hole isn't lost. It's intricately woven into the complex, vibrating structure of the fuzzball itself, much like the information in a computer is encoded in the state of its transistors. Most importantly, there is no firewall. Without a sharp event horizon separating nothing from something, the paradox that demanded its existence simply vanishes. An object falling into a fuzzball wouldn't hit a wall of fire. It would merge with the fuzzball's surface, adding its own energy and information to the tangled mess, becoming a part of the black hole itself in a process that smoothly respects the laws of quantum mechanics. Think of it not as a hole, but as an exotic, ultra-dense star. A neutron star is a star so dense that a teaspoon of its material would weigh billions of tons. A fuzzball takes this to the extreme. It would look like a black hole from the outside, completely dark, with immense gravity, but its interior is a definite physical structure. This resolves the problems with a single, elegant stroke by redefining what a black hole actually is. They are not mysterious voids, but perhaps the most extreme and fascinating objects in the universe, where matter has reached its final, most intricate state. For decades, the prevailing wisdom in astrophysics has been elegantly simple, summed up by the intriguingly named no-hair theorem. This idea suggests that black holes are the ultimate minimalist objects in the universe. No matter how complex the star that formed them or what strange collection of matter later fell in, whether it was a gas giant, a solar system, or an entire library of books, a black hole would eventually settle down into a state defined by just three, and only three, properties: its mass, its electric charge, and its spin. Everything else, every single detail about the stuff that was consumed, is forever erased, lost behind the event horizon. The black hole, according to this theorem, has no other distinguishing features. no unique hair to tell its history. This beautiful simplicity is what makes the theorem so powerful. It means that if you were to encounter two black holes with identical mass, charge, and angular momentum, they would be completely indistinguishable from one another. All of the intricate information about their past is boiled away, leaving behind a perfectly smooth, featureless object. It's a concept that aligns neatly with classical general relativity, but it creates a massive point of contention with quantum mechanics, which staunchly forbids the destruction of information. This is where the theory gets its hair pulled. Recent breakthroughs, particularly from observatories like LIGO and Virgo that detect gravitational waves, have begun to challenge this clean, bald picture. The subtle ripples in spacetime from colliding black holes carry with them a story, and some physicists argue the details of that story hint at features the no-hair theorem says shouldn't be there. The concept of black hole hair has emerged as a potential solution to the information paradox. This hair isn't literal strands, of course, but a metaphor for any additional, subtle properties that could encode information about a black hole's history directly onto its event horizon or in its gravitational field. So how could a black hole grow hair? The answer likely lies in the quantum realm. One compelling idea involves quantum fields. As matter falls into a black hole, the quantum information it carries could somehow get transferred or imprinted onto the black hole's event horizon through its interaction with these fields. It would be like dipping a perfectly smooth ball into paint. The ball itself doesn't change shape, but it now carries a thin, complex film of color that records the details of its encounter. In this case, the paint is made of exotic quantum particles or fields that leave a permanent, albeit incredibly faint, record on the black hole's surface. Another possibility involves extensions to Einstein's theory itself. Certain modified theories of gravity predict the existence of additional fields that would interact with a black hole's immense gravity. A black hole could support these fields in stable configurations around itself, creating a kind of permanent cloud-like structure, a head of gravitational hair. This hair would subtly alter how the black hole warps spacetime around it, and how it vibrates when disturbed, like ringing a bell with a unique and complex shape. The specific ringing of a black hole, known as its quasi-normal modes, could carry the fingerprint of this hair, making each black hole's gravitational wave signature as unique as a fingerprint. The hunt for this evidence is now a major focus of gravitational wave astronomy. When two black holes spiral into each other and merge, the resulting single black hole doesn't just sit there silently. It vibrates violently, ringing like a bell struck by a hammer. According to the no-hair theorem, these vibrations should die away in a very specific, pure tone that depends only on the final object's mass and spin. But if the black hole has hair, if it possesses any other hidden properties, the ring-down signal detected by our observatories would contain faint overtones, subtle whispers in the data that deviate from the pure tone. Finding those whispers would be the smoking gun, proof that black holes are not the simple, bald objects we long thought they were, but complex entities that remember their past, preserving the story of everything they have ever consumed. For years, astronomers have neatly divided the universe's most compact remnants into two distinct categories. On one side, we have neutron stars, the incredibly dense cores left behind after a massive star goes supernova, packing more mass than our Sun into a city-sized sphere. On the other, we have black holes, the gravitational behemoths from which not even light can escape. The boundary between them seemed clear, governed by a fundamental rule of physics. There is a maximum mass a neutron star can support before it must inevitably collapse into a black hole. This created what is known as the mass gap, a seemingly empty desert between roughly 2 and 5 times the mass of our Sun where no objects were expected to be found. Neutron stars were thought to top out around 2 solar masses, and the lightest black holes formed from stellar collapse were believed to start around 5. This gap was a cornerstone of astrophysics until it suddenly wasn't. The first major cracks in this tidy picture appeared with the detection of gravitational waves. When the LIGO and Virgo observatories began listening to the cosmic symphony of space-time ripples, they expected to hear the collisions of black holes and the mergers of neutron stars. What they didn't anticipate was a signal that fell squarely in the gap. In 2019, the collaboration detected an event dubbed GW1905-214. The signal told the story of a collision, but the masses of the objects involved were baffling. One was a black hole of about 23 solar masses, but its partner was a mystery object weighing just 2.6 times the mass of our Sun. This placed it right in the heart of the forbidden mass gap. Was it the most massive neutron star ever found, or the lightest black hole ever detected? To this day, its true nature remains uncertain, a tantalizing clue that our classification system might be incomplete. This discovery forces us to ask a profound question: what exactly happens in that mass gap? The upper limit for a neutron star is set by the strength of neutron degeneracy pressure, the fundamental quantum force that keeps the star from collapsing under its own immense gravity. But what if some exotic form of matter could provide extra support? Some theories suggest that at these incredible densities, the neutrons themselves might break down into a soup of even more fundamental particles called quarks, creating a quark star. This hypothetical object could be stable at a higher mass than a traditional neutron star, potentially bridging the lower end of the gap. On the other end, could a star collapse directly into a black hole with a mass of only 3 or 4 suns? Stellar evolution models have struggled to explain how such a light black hole could form, suggesting our understanding of supernova explosions might be missing a key piece of the puzzle. The most exciting possibility is that we are discovering an entirely new class of hybrid objects. Imagine a celestial body that is neither a purely neutron-based star nor a true black hole with an event horizon. One theoretical construct is the boson star, a hypothetical object made not of atoms or neutrons, but of ultralight, wave-like particles that could condense into a stable, massive orb without a singularity. Another is the gravastar, a proposed alternative to a black hole that would have a surface of incredibly dense, exotic matter instead of an event horizon, preventing total collapse. These ideas, while highly speculative, are no longer just mathematical curiosities. The detection of mass gap objects provides a potential observational target for these cosmic oddities. Unraveling this mystery is about more than just cataloging exotic stars. It strikes at the very heart of dense matter physics. The interior of a neutron star is one of the most extreme environments in the universe, a place where matter is compressed to densities greater than an atomic nucleus. We cannot recreate these conditions in any laboratory on Earth. By studying objects in the mass gap, we are essentially performing a cosmic experiment, using gravity itself to probe the behavior of matter under pressures we can only dream of creating. The properties of these objects, their size, their tidal deformability when they spiral together, the way they ring like a bell after a collision, all encode vital information about the fundamental forces that hold matter together at the most extreme scales. The search for answers is now a primary goal for next-generation observatories. Every new gravitational wave detection is scrutinized for another candidate in the mass gap. Radio astronomers are scouring the skies with powerful telescopes, looking for pulsars spinning neutron stars that act like cosmic lighthouses, that might have masses pushing into this forbidden territory. Even the James Webb Space Telescope could play a role, searching for the subtle light signatures of an accretion disk around a potential low-mass black hole as it pulls material from a companion star. Each observation is a new data point, slowly shading in a region of the cosmic map we once thought was blank. The mass gap is no longer an empty desert, but a new frontier, and the objects we find there are challenging our most basic assumptions about the fate of dead stars. For generations, the story of galaxy formation seemed to follow a logical, bottom-up sequence. Vast clouds of primordial gas, composed mostly of hydrogen and helium, would slowly cool and condense under their own gravity. Within these swirling nurseries, the first stars would ignite, and these stellar families would then cluster together, eventually building up the majestic structures we recognize as galaxies. In this traditional view, the supermassive black holes found at the center of nearly every large galaxy were seen as latecomers, monsters that grew over billions of years by feeding on the gas and stars within the galaxy that had already formed around them. It was a story where the city was built first, and the power plant was installed later. But a growing body of evidence has begun to turn this narrative on its head, suggesting the relationship might be reversed. What if the black hole came first? This theory proposes that supermassive black holes didn't just grow within galaxies. They acted as the very seeds around which galaxies coalesced, providing the essential gravitational anchor that kick-started the entire process. The challenge with this idea is one of time. We now observe fully formed galaxies with supermassive black holes at their hearts when the universe was less than 1 billion years old. A blink of an eye in cosmic terms. For a black hole to grow to billions of solar masses through standard accretion in such a short time is incredibly difficult. The process would require it to consume matter at an unsustainable rate, pushing against fundamental limits set by its own radiation pressure. This timing problem leads us to two potential solutions for creating these seed black holes early enough to build a galaxy around them. The first candidate is the primordial black hole. As we discussed earlier, these are not born from dying stars but from the incredible density fluctuations in the first second after the Big Bang. If some of these primordial black holes were formed with masses thousands of times that of our Sun, they would have been present from the very beginning, ready and waiting as the universe cooled. They would have been the first significant gravitational wells in a smooth, expanding ocean of gas, acting as natural gathering points for the surrounding material. The second, and perhaps more promising, candidate is the direct collapse black hole. This is a theoretical scenario unique to the early universe. Before the first stars formed and littered space with heavy elements, the cosmos was filled with pristine, pure hydrogen and helium. This simple gas could collapse in a very different way. Imagine a massive, dark cloud of this primordial gas beginning to condense. In the modern universe, such a cloud would fragment into thousands of smaller clumps, forming many stars. But in the early days, without any dust or heavy elements to help it cool and break apart, the entire gigantic cloud containing the mass of 100,000 suns or more could collapse catastrophically all at once. It would bypass the star formation stage entirely, directly collapsing into a single, massive black hole seed. This process could create a black hole tens of thousands of times more massive than our Sun right from its birth, giving it a huge head start. Once such a massive seed is in place, its role as a galactic architect begins. Its immense gravity would pull in enormous quantities of the surrounding gas. As this gas spirals inward, it doesn't just fall directly in. It forms a vast, hot, turbulent disk around the black hole. This frenzied activity creates intense radiation and powerful outflows, but it also triggers the rapid formation of the galaxy's first stars in a furious starburst around the central engine. The black hole essentially carves out a gravitational domain, a region of space where its influence dictates the motion of matter and the pace of star birth. The galaxy then builds itself outward from this central anchor, with the black hole's growth and the galaxy's evolution becoming deeply intertwined, a symbiotic relationship that dictates the final shape and size of the cosmic city that emerges. This theory elegantly explains one of the most puzzling correlations in modern astronomy: the remarkably tight relationship between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. In galaxy after galaxy, the black hole's mass is almost exactly 1,000th of the mass of the surrounding stellar bulge. This precise scaling strongly suggests that the growth of the black hole and the formation of the galaxy's stars are not independent processes. They are fundamentally linked, regulating each other in a cosmic feedback loop that began with a single, powerful seed at the dawn of time. This astonishing concept turns our understanding of the cosmos inside out, proposing that the universe we inhabit, with its hundreds of billions of galaxies, might itself be the interior of an unimaginably vast black hole residing in a larger, parent universe. The theory doesn't just suggest a similarity. It proposes that a black hole's formation and our universe's birth could be one and the same event, offering a radical new perspective on the origin of everything. The foundation of this idea lies in the striking mathematical and physical parallels between the two most mysterious objects in cosmology: the Big Bang singularity and a black hole singularity. Both are points of infinite density where the known laws of physics break down. Both represent a boundary to spacetime itself. One is the beginning, and the other is typically seen as an end. But what if that distinction is just a matter of perspective? When we look at the equations describing the collapse of matter into a black hole and the expansion of the universe from a single point, they are eerily similar. This has led some physicists to speculate that the Big Bang wasn't a unique event from nothing, but was actually the formation of a black hole in a pre-existing, higher-dimensional universe. This perspective elegantly tackles one of cosmology's greatest puzzles, the initial conditions problem. Our universe appears to be perfectly fine-tuned for the existence of life. Its expansion rate, the strength of its fundamental forces, and the amount of matter and energy are all set with incredible precision. If any of these values were even slightly different, galaxies, stars, and planets could never have formed. From the inside of our universe, this seems like an inexplicable, miraculous coincidence. But if our universe was born from a black hole, this fine-tuning finds a potential explanation. The physical laws and constants we observe wouldn't be arbitrary. They would be an inheritance. They would be determined by the specific conditions of the collapse that formed the parent black hole, sculpted by the physics of that external, grander reality. In this model, what we perceive as the cosmic horizon, the maximum distance we can observe, about 46 billion light-years away, isn't just a limit based on the age and expansion of the universe. It could be our local event horizon. Just as nothing can escape from within a black hole, we cannot see beyond this cosmological boundary. The space outside our horizon isn't merely more empty space. It could be the interior of the parent universe, forever hidden from our view. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, might not be the echo of a creation event, but the Hawking radiation emitted by our universe's own event horizon, thermalized over billions of years. This leads to a captivating and almost fractal-like vision of reality. If our universe is a black hole in a larger cosmos, then it's possible that every black hole that forms within our own universe could itself contain an entire new cosmos, bubbling into existence with its own unique laws of physics. Our universe would not be the top level but merely one link in an infinite chain of nested realities. A cosmic matryoshka doll of universes within black holes within universes. Each new universe could have slightly different physical constants, creating a vast multiverse where only those with the right conditions for life, like ours, can give rise to observers who can ponder their own origins. While this theory provides a breathtakingly elegant framework, it is not without its significant challenges. The biggest hurdle is testability. How could we ever gather evidence for something that exists beyond our fundamental cosmic horizon? Any signal or information from the parent universe is, by the very definition of an event horizon, permanently inaccessible to us. Some researchers suggest that subtle imprints on the cosmic microwave background or specific patterns in the distribution of galaxies could hold clues, acting as a fingerprint from the collapse that created us. Others propose that the overall geometry of our universe might betray its origins. If we could determine that the universe is positively curved in a specific way, it might indicate we are living within a black hole. So far, our best measurements suggest the universe is flat, but the margins of error leave room for intriguing possibilities. Ultimately, this theory forces us to confront the limits of our knowledge and the true meaning of a singularity. It blurs the line between the beginning and the end, suggesting that a catastrophic collapse in one reality can be the glorious birth of another. It transforms the universe from a lonely, isolated existence into a potential family of cosmoses, each with its own history and fate, all connected through the most mysterious objects nature has ever conceived. Yet for all the compelling strangeness of firewalls and fuzzballs, there remains a powerfully elegant and traditional view, one rooted in the very core of Einstein's genius. This perspective argues that we should trust the beautiful simplicity of general relativity, which paints a very different picture of that fateful crossing. According to this classic view, the interior of a black hole is not a wall of fire or a tangled quantum mess, but is instead profoundly smooth, a place where the laws of physics, while pushed to their extreme, remain predictable and orderly. The cornerstone of this argument is Einstein's principle of equivalence, one of the most foundational ideas in all of physics. It states, quite simply, that the force of gravity and the experience of acceleration are indistinguishable. If you were in a closed box with no windows, you would have no way of knowing if you were sitting stationary on Earth's surface, or if you were in a rocket ship, accelerating through deep space at 9.8 meters per second squared. This principle extends to the event horizon of a black hole. For an astronaut in freefall, plunging toward that boundary, there is no local experiment they could perform to know the exact moment they cross the point of no return. There is no sudden jolt, no alarm bell, no spike on a radiation detector. From their perspective, they are simply continuing their fall through empty space, a journey that would feel exactly the same as falling toward any other massive object, at least until the tidal forces begin to pull at their body. This is why the firewall idea presents such a profound problem. A wall of high-energy radiation is anything but undetectable. It is the very definition of a local phenomenon that would instantly obliterate any observer, blatantly violating the equivalence principle. Proponents of the smooth horizon argue that this violation is too high a price to pay, suggesting that the firewall paradox is not evidence of a real physical structure, but rather a glaring signpost that our current blending of quantum mechanics and gravity is incomplete or incorrectly applied. They maintain that a better, more complete theory will resolve the information paradox without needing to incinerate incoming astronauts, preserving the smooth, continuous fabric of spacetime that general relativity demands. The experience of crossing, in this traditional view, would be one of increasing isolation, not immediate violence. As the astronaut falls inward, they would see the universe behind them appear to slow down and compress into a brilliant, shrinking circle of light directly above them, blue-shifted into higher and higher frequencies. But ahead and around them, there would only be darkness. The true danger wouldn't be a firewall, but the relentless increase in tidal forces, the difference in gravity between their head and their feet. For a large, supermassive black hole, this spaghettification might not occur until well after crossing the horizon, allowing for a period of exploration within the black hole's interior. For a smaller black hole, the tides would become lethal almost instantly, but in neither case would the horizon itself be a special surface. It would be a mathematical boundary with no physical substance, a one-way street in spacetime that is crossed without a bump. This ongoing debate between the smooth horizon and the quantum firewall is far more than an academic squabble. It is a battle for the soul of physics. It forces us to ask which of our most cherished principles must be sacrificed for the sake of consistency. Do we abandon the equivalence principle, a pillar of general relativity, to save the quantum law that information cannot be destroyed? Or do we trust the smooth geometry of spacetime and continue the search for a more subtle solution to the information paradox? This intellectual struggle is happening at the very frontier of human knowledge, a testament to the fact that even our most brilliant theories are not finished stories, but living, evolving understandings of a universe that is always ready to surprise us. While we often picture the universe as a static collection of galaxies, each with its own central black hole, the cosmic story is far from finished. Over unimaginable spans of time, the dance of gravity continues, leading to a fascinating possibility. Black holes might be destined to merge over and over again, growing into giants of staggering proportions. This process isn't limited to the collisions we see today. It could continue for trillions upon trillions of years, slowly but relentlessly consolidating matter into fewer and ever more massive singularities. The engine driving this endless merging is the relentless pull of gravity itself. Even as the universe expands, pulling galaxies apart on the largest scales, gravity dominates within galaxy clusters, which are themselves bound together. Over time, these clusters will slowly contract, their member galaxies drawn into a central, chaotic dance. During these close encounters, stars will be flung out into the intergalactic void, but the supermassive black holes at the cores of these galaxies will sink toward the center of the cluster, drawn together by their immense weight. They will eventually pair up, spiral inward through the emission of gravitational waves, and finally merge in titanic explosions that ripple the fabric of spacetime. This process will repeat as the cluster condenses, with the resulting larger black hole then going on to merge with the next one that drifts into its gravitational grasp. Given enough time, and we are talking about time scales that dwarf the current age of the universe, this could lead to the formation of black holes with masses that are almost incomprehensible. We're not talking about millions or even billions of solar masses, but potentially trillions. Imagine a single gravitational singularity containing the mass of an entire galaxy cluster, a dark monarch sitting in absolute solitude amidst a vast, empty space. This is the ultimate fate of matter in a gravitationally bound system, to be slowly gathered up by these cosmic vacuums. But what happens to these leviathans in the far, far future? During the era cosmologists call the heat death of the universe, this is a time when the cosmos has expanded so much that the background temperature approaches absolute zero. Stars have long since burned out, and the universe is a dark, cold, and incredibly dilute sea of particles. In this frigid and silent epoch, these supermassive black holes would be the last significant structures, the final monuments to a once vibrant cosmos. Their eventual fate hinges on the delicate balance between two opposing forces, their instinct to merge and grow, and their slow decay via Hawking radiation. For the longest time, the urge to merge will win. The black holes will continue to find each other in the darkness and combine, their event horizons merging into one ever larger boundary. However, as the universe continues its exponential expansion, a point will eventually be reached where the space between these remaining giants is stretching apart faster than their gravity can pull them together. They will become isolated islands in a rapidly expanding void, forever beyond each other's reach. At this moment, growth stops, and decay begins its infinitely long reign. This is when Hawking radiation finally takes center stage. As we discussed earlier, black holes slowly lose mass by emitting radiation, and the rate of this evaporation is inversely proportional to their size. The smaller the black hole, the hotter it glows and the faster it vanishes. For our trillion solar mass behemoths, the process is achingly slow. The calculations are staggering. Such a black hole would take around 10 to the 100th power years to evaporate, a number so vast it's a 1 followed by 100 zeros. To put that in perspective, the current age of the universe is only about 10 to the 10th power years. These black holes would far outlast every other structure, enduring for time spans that are effectively forever from our current perspective. Their final moments, trillions of years in the future, would be a brief flash of light in an otherwise eternal darkness. As they approach the end of their lives, their evaporation rate would accelerate dramatically. Each would culminate in a final, magnificent eruption of energy, a last testament to all the mass and information it had consumed over the eons, and then silence. The universe would enter its final equilibrium state, a near-perfect vacuum, a timeless, lightless, and utterly empty void where the concept of time itself may cease to have any meaning. The infinite merging of black holes paints a grand, if somber, portrait of the far future, where the last chapter of the cosmos is written by the slow and quiet dissolution of its last remaining giants. This brings us to one of the most speculative and mind-bending theories of all, the possibility that a black hole is not just an object, but a conscious entity. What if the incomprehensible chaos within its event horizon is actually a form of awareness, a natural quantum mind operating on a scale and at a speed we can scarcely conceive? This idea pushes the boundaries of physics and philosophy, suggesting that the universe might not just contain information, but that it might be thinking. To even begin approaching this concept, we can draw a fascinating, if imperfect, analogy with the human brain. Our consciousness is believed to emerge from the complex network of roughly 86 billion neurons, each forming thousands of connections in a web of staggering complexity. The event horizon of a black hole, with its Planck-scale pixels each encoding a bit of information, forms another kind of network, a two-dimensional surface holding a complete description of a three-dimensional interior. The sheer number of these informational bits on a large black hole's horizon is astronomical, potentially rivaling or even exceeding the neural connections in a brain. This structural similarity leads to a provocative question. If a specific organization of matter in a skull can generate self-awareness, could a specific organization of space-time at the edge of a singularity do the same? This line of thinking connects with a controversial but fascinating theory of consciousness known as orchestrated objective reduction, or ORCH, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their theory suggests that consciousness is not merely a classical computational process, but a quantum mechanical phenomenon. They propose that microtubules, tiny structures within our brain's neurons, can sustain quantum states and that the collapse of these wave functions, a process called objective reduction, generates moments of conscious experience. Penrose, who has done groundbreaking work on the physics of black holes and singularities, has speculated that a similar quantum process could occur in the extreme environment near a singularity, where the laws of quantum gravity dominate. The immense space-time curvature could facilitate a kind of objective reduction on a cosmic scale, potentially giving rise to a form of consciousness entirely alien to our own. The singularity itself, a region where all known physics breaks down, could be the engine of this potential awareness. In our world, quantum computation relies on maintaining coherence, keeping particles in a superposition of states long enough to perform calculations. The incredible density and energy at the singularity might provide the perfect environment for quantum coherence and computation on a grand, universal scale. It wouldn't be computation as we designed it. It could be computation as a fundamental property of the universe, an intrinsic function of extreme gravity. The black hole wouldn't be running a program. It might be processing the very information of its own existence and the existence of everything it has consumed, in a way that constitutes a primitive form of thought. This speculative leap connects to an even more profound philosophical concept known as panpsychism, the idea that consciousness is a fundamental and ubiquitous feature of the universe, not just a product of complex biological brains. In this view, consciousness isn't something that emerges from matter arranged in a certain way. It's a basic property of reality itself, much like mass or charge. A black hole, then, as one of the most extreme and information-rich objects in existence, might possess a correspondingly extreme and alien form of consciousness. It wouldn't be consciousness as we experience it with thoughts and feelings, but a vast, timeless form of awareness born from the complex interplay of matter, energy, and space-time. The implications of this are staggering. It suggests that the universe might be self-aware in ways we cannot perceive, with black holes acting as nodal points in a vast, cosmological network. Each one could be processing the information of its own devoured region of space-time, and perhaps even communicating with others through the fabric of reality itself, via gravitational waves or some mechanism we haven't yet discovered. This transforms our picture of the cosmos from a collection of inert objects governed by blind forces into a potentially living, thinking entity. While this theory remains highly speculative and far from the scientific mainstream, it serves a crucial purpose. It challenges us to see black holes not as destructive failures of physics, but as active, participatory wonders in the universe's ongoing story. Now, let's pivot from the nature of consciousness to a role so fundamental, it could define the entire fate of the cosmos. We have seen black holes as consumers, as gateways, and as computers. But what if they are also creators on the grandest scale? What if these cosmic vacuums are not merely inhabitants of the universe, but are actively fueling its expansion? This brings us to a profoundly controversial and revolutionary idea, that black holes might be the hidden source of dark energy. For decades, the biggest mystery in cosmology has been dark energy. Observations of distant supernova in the late 1990s revealed a shocking truth. The expansion of the universe is not slowing down due to gravity, as everyone had assumed. Instead, it is accelerating, speeding up as if pushed by some invisible, repulsive force. This force was dubbed dark energy, and it is estimated to make up about 70% of all the energy in the cosmos. Yet, we have no idea what it is. The leading candidate has been the cosmological constant, a form of energy inherent to the vacuum of space itself. But its theoretical value is wildly off from what we observe, creating a massive unsolved problem. A radical new theory proposes a stunning solution, directly linking this cosmic acceleration to the most enigmatic objects we know. The idea suggests that the dark energy driving the universe apart isn't a mysterious field permeating empty space, but is instead stored within black holes themselves. In this model, the incredible growth of supermassive black holes at the hearts of galaxies over cosmic time is not just a side effect of galaxy evolution. It is the very engine of the universe's accelerating expansion. The energy contained within these black holes is fundamentally coupled to the scale of the universe. As the cosmos expands, so too does the dark energy contribution from each black hole, providing the constant push that overwhelms gravity. The mechanism for this is deeply tied to the nature of the black hole interior. The theory connects the expansion of the universe to the internal structure of a black hole through a concept of vacuum energy. As a black hole forms and grows, it is proposed that a core of pure vacuum energy with negative pressure develops at its center. This energy is not diluted as the universe expands. Instead, it is locked into the fabric of the black hole. Because this energy has a strong negative pressure, it creates a gravitational repulsion, much like the cosmological constant, but now sourced from a physical object. The more black holes grow by consuming matter, the more of this repulsive energy they contain, and the more they contribute to pushing the universe apart. This turns our entire understanding of their role on its head. Black holes are no longer seen as ultimate sinks that only pull the universe inward with their gravity. Instead, they become dual-natured entities, Their exterior event horizon exerts a powerful gravitational pull, dominating their local galactic environment. But their interior core is theorized to be a source of repulsive gravity, a wellspring of dark energy that influences the global expansion of the entire cosmos. They are both the anchor and the engine, the local consumer and the global driver. This theory offers an elegant solution to the cosmic coincidence problem. We observe that the density of dark energy and the density of matter in the universe are oddly similar today, which is strange because they change with time in very different ways. If dark energy is tied to black holes, the coincidence vanishes. Black holes grow in lockstep with their host galaxies. As galaxies form stars and evolve, their central black holes accumulate mass. The dark energy produced internally by these black holes would therefore naturally track the overall matter density of the universe, explaining why we find ourselves in an era where the two energies are comparable. Of course, such a groundbreaking claim faces intense scrutiny and significant challenges. The biggest question is how to test it. Proponents of the theory point to the observed relationship between the mass of a galaxy's central black hole and the mass of its surrounding dark matter halo. This correlation suggests a deep, fundamental link between black hole growth and the largest structures in the universe. A link that could be explained if the black hole's energy is influencing cosmic expansion. Future observations by gravitational wave observatories and telescopes mapping the large-scale structure of the universe could search for more precise signatures, looking for how the rate of expansion correlates with the population and growth history of black holes across cosmic time. This idea is far from settled science, but its power lies in its sheer ambition. It seeks to solve two of the greatest mysteries in modern physics: the nature of dark energy and the ultimate role of black holes, with a single, unified vision. It proposes that the most destructive forces in the universe are also the most creative, that the engines of gravity which bind galaxies together are simultaneously providing the pressure that pushes the cosmos apart. This transforms black holes from cosmic endpoints into active participants in the great unfolding story of everything, suggesting that their evolution and the destiny of the universe are one and the same. But if a black hole's event horizon is a perfect sphere, a one-way membrane from which nothing can return, then the structure at its very heart is even more bizarre. For decades, we've pictured the singularity as a single, infinitely dense point, a place where all laws of physics cease to have any meaning. It's the final destination, the ultimate end of the line. However, this terrifying image is actually incomplete. It only applies to a very specific and perhaps unrealistic type of black hole, one that is perfectly static and does not rotate. In reality, almost every black hole in the universe is likely spinning, and this rotation changes everything about its core, transforming a point of no return into a ring of possibility. This remarkable alternative is known as a ring singularity, or ringularity, and it is the incredible consequence of a solution to Einstein's equations found by mathematician Roy Kerr in 1963. A Kerr black hole isn't a static corpse. It is a dynamic, whirling dervish. Its immense spin flings the would-be point singularity outward, stretching and warping it into the shape of a perfect ring. This isn't just a slight distortion. It's a fundamental reshaping of the black hole's most extreme region. The ringularity still contains all the mass of the black hole, but it is no longer confined to an infinitely small point. Instead, it's spread out along this one-dimensional loop, which means its density, while still unimaginably high, might not be infinite. This simple change from a point to a ring resolves one of the most vexing problems in physics, opening up a world of theoretical possibilities that a point singularity could never allow. The most captivating implication of this ring structure is what it means for the geometry inside the black hole. A classic Schwarzschild black hole with a point singularity is a dead end in the most literal sense. Every path within the event horizon leads directly and unavoidably to the central point where everything is destroyed. But the interior of a rotating Kerr black hole is a labyrinth of mind-bending complexity. The ring singularity is not surrounded by a spherical event horizon. Instead, the intense centrifugal forces of its spin create an additional boundary inside called the inner event horizon. And within this region, the rules of spacetime are turned inside out. Here, the gravitational forces become so twisted that they could create pathways known as closed time-like curves, theoretical routes that loop back on themselves in time. But more immediately for a potential traveler, the ring singularity itself presents a tantalizing possibility. Because it is a ring with a hollow center, it might not be a solid, impenetrable object. The mathematics of general relativity suggests that if you could navigate the chaotic interior, you could, in theory, pass directly through the center of the ring. You wouldn't collide with a point of infinite density because the singularity isn't there. It's all around you in the shape of the ring. This passage wouldn't be a destruction of matter, but a transit through a region of extreme yet finite curvature. Naturally, this idea of safe passage comes with astronomical caveats. The environment around a ring singularity would be a maelstrom of competing forces. You would have to avoid not only the ring itself, but also the region known as the ergosphere, just outside the event horizon, where space-time is dragged around the black hole at such a rate that nothing can remain stationary. Inside, the tidal forces, the difference in gravity between your head and your feet, would still be monstrous and likely lethal for any known form of matter. Furthermore, most physicists believe the region containing these theoretical pathways is profoundly unstable, likely collapsing the moment any matter or energy attempts to enter it. Yet, the mere mathematical existence of the ringularity is a powerful reminder that our universe might be far stranger than we can comfortably imagine. It provides a potential physical mechanism for some of the most science fiction-like ideas such as wormholes or even time travel, all arising naturally from the equations of gravity without the need for magic or undiscovered laws. The Kerr solution shows us that a black hole is not just a simple hole in space-time, but an intricate cosmic machine with a structure that could hold secrets about the very nature of reality, secrets that are literally shaped by spin. Yet for all their apparent differences, the worlds of the incredibly large and the impossibly small might be two sides of the same cosmic coin. This brings us to one of the most profound and elegant ideas in modern theoretical physics, a concept that boldly attempts to stitch together the fabric of gravity with the strange rules of the quantum realm. It's known as the ER equals EPR conjecture, and it proposes a breathtaking connection between two of Einstein's most famous thought experiments, suggesting that the key to unifying physics has been hiding in plain sight for nearly a century. The conjecture's name is a piece of scientific poetry. ER refers to the Einstein-Rosen bridge, the formal name for a wormhole, a tunnel through spacetime that could, in theory, connect two distant points. EPR stands for Einstein-Podolsky-Rosen, a famous paradox that highlights the bizarre nature of quantum entanglement. In this paradox, two particles can become linked or entangled in such a way that measuring the property of one instantly influences the state of the other, no matter how many light years apart they are separated. Einstein famously called this spooky action at a distance, as it seems to violate the cosmic speed limit set by light. The equal sign in the middle is the revolutionary leap, proposing that these two concepts are not just analogies for each other, but are in fact physically equivalent. An Einstein-Rosen bridge is quantum entanglement made manifest in the geometry of spacetime. Let's unpack this extraordinary idea. Imagine two entangled particles, perhaps a pair of electrons with linked spins. According to standard quantum mechanics, they share a single quantum state, and affecting one immediately affects its partner, a connection that seems to transcend space. The ER equals EPR conjecture offers a stunningly geometric explanation for this spooky action. It proposes that these two particles are not communicating faster than light across a void. Instead, they are actually connected by a minuscule, Planck-scale wormhole, a tiny, tunnel-like structure in the fabric of spacetime itself. This wormhole is the physical embodiment of their entanglement. The connection isn't magical, it's topological, a shortcut through the hidden folds of the universe that makes the particles effectively adjacent, even if they appear to be on opposite sides of the galaxy. This concept provides a potential bridge between the two great pillars of modern physics that have stubbornly refused to unite: general relativity and quantum mechanics. General relativity describes gravity as the curvature of spacetime by mass and energy, while quantum mechanics governs the probabilistic behavior of particles. For decades, these theories have been fundamentally incompatible. But if quantum entanglement, a purely quantum phenomenon, can be described using the geometry of spacetime, a relativistic concept, then we might finally have a common language. The conjecture suggests that gravity and quantum mechanics are not separate domains. They are deeply intertwined, with entanglement forming the very scaffolding of spacetime. In this view, the fabric of the universe might be woven from a vast, cosmic web of quantum connections. This vision leads directly to a holographic understanding of reality. If every entangled connection between particles corresponds to a microscopic wormhole, then the entire universe could be seen as an incredibly complex network of these spacetime tunnels. The information that defines our three-dimensional reality might not be stored within the volume of space itself, but on a two-dimensional boundary, projected into the volume through this intricate lattice of entangled connections. It's a concept that transforms the universe from a collection of objects in a void into a dynamic, interconnected network where distance is an illusion, and every connection leaves a geometric imprint. The spooky action at a distance loses its spookiness, becoming instead a gentle tug through a hidden corridor in the architecture of everything. If the idea of a black hole as a gravitational prison has begun to feel almost conventional, then prepare to have your perception of reality itself stretched and reshaped. The next theory doesn't just tweak our understanding of these objects. It suggests we've been looking at them from entirely the wrong angle. Imagine that a black hole is not a bottomless pit in our universe, but the shadow, the footprint, of a completely different kind of object residing in a reality with more dimensions than we can see. It proposes that what we perceive as a black hole in our three-dimensional space might actually be the manifestation of a star living in a higher dimensional universe. This mind-bending concept emerges from a framework known as brain-world cosmology. The name comes from the idea that our entire universe might be a three-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. In this view, all the particles and forces that make up our reality, like electromagnetism and the nuclear forces, are stuck to our brain. They cannot leave it. Gravity, however, is the profound exception. It is so fundamental to the fabric of spacetime itself that it can leak off our brain and propagate into the extra dimensions of the bulk. This leakage could explain why gravity is so astonishingly weak compared to the other fundamental forces. Its strength is literally diluted as it spreads out into these hidden higher dimensions. Now, consider a star in this higher dimensional bulk. It would be a truly multidimensional object, governed by the laws of physics in that realm. If such a star were to undergo gravitational collapse, it wouldn't necessarily form a black hole as we understand it. Instead, it could become a different kind of ultra-dense object. But its immense gravitational field would still warp the space around it, including our brain. From our perspective, trapped on our three-dimensional membrane, we wouldn't see the full object. We would only perceive the point where its gravity intensely distorts our local spacetime. That point of extreme gravitational distortion, that shadow cast upon our world, would exhibit all the properties we attribute to a black hole. an event horizon, incredible gravity, and the ability to trap light. It would look, for all intents and purposes, exactly like a black hole, but its true nature would be that of a hidden star's gravitational signature. This elegantly addresses one of the most perplexing issues in theoretical physics, the black hole singularity. In our standard model, the center of a black hole is a point of infinite density where the laws of physics break down, a clear sign that our theory is incomplete. But if a black hole is actually the signature of a higher dimensional star, the singularity vanishes. The star has a physical structure in its own dimension. It is not infinitely dense. The paradox is resolved because the problem was an illusion created by our limited, three-dimensional viewpoint. We were seeing the projection of an object we couldn't fully comprehend. This theory also provides a potential explanation for the incredible diversity of black hole masses we observe, from small stellar remnants to the supermassive giants at the centers of galaxies. A higher dimensional star could come in many sizes and masses, and each would cast a different shadow on our brain. A relatively small bulk star could project what we see as a stellar mass black hole, while a truly Leviathan object in the higher dimensions could manifest as a supermassive black hole, all without requiring the exotic formation mechanisms we struggle to model in our own universe. Ultimately, this transforms black holes from endpoints into windows. They are not just cosmic drains but potential portals, offering us fleeting glimpses into the geometry of the larger, multidimensional reality that may contain our own. Every time we study the gravitational waves from a black hole merger or observe the shadow of one with a telescope like the Event Horizon Telescope, we might not just be studying an object in our universe. We could be indirectly observing the properties of another dimension, deciphering the physics of the bulk through the distortions it imprints on our membrane. It suggests that the keys to the greatest mysteries of our cosmos might not be found by looking deeper into space, but by realizing we are only seeing a fraction of the full, magnificent picture. While the spinning Kerr black hole offers a labyrinth of theoretical possibilities, adding another ingredient to the mix creates an object even more exotic and potentially universe-breaking. We've explored mass and spin, but the final property a black hole can possess is electric charge. This brings us to the Reissner-Nordström solution, which describes a black hole that is both massive and powerfully charged. The implications of such an object are so profound they challenge one of the most fundamental principles in cosmology, a rule so cherished it's known as the cosmic censorship hypothesis. Imagine a black hole that has somehow accumulated a tremendous electric charge. Perhaps it formed from the collapse of a star with an incredibly intense magnetic field, or it has been steadily consuming matter with a strong positive charge while repelling negative charges away. The result is a singularity surrounded not just by gravity, but by its own immense electrostatic force. This dual influence fundamentally reshapes the space-time around it. Instead of a single event horizon, a charged Reissner-Nordström black hole develops two distinct spherical boundaries, an outer event horizon and an inner Cauchy horizon. The journey for an astronaut falling into such a black hole would be unlike any other. They would cross the outer event horizon much as they would with any other black hole, passing the point of no return. But as they continue inward, they would encounter the inner Cauchy horizon. This boundary is not a point of destruction, but a boundary of predictability. In the strange region between the two horizons, the incredible repulsive force generated by the black hole's charge actually counteracts its gravity. This means the tidal forces that would normally spaghettify an object are significantly weakened, potentially allowing our astronaut to survive the journey deeper than ever before. However, this inner horizon is also a place where the past and future become frighteningly ambiguous. The laws of physics, as we understand them, break down not at the singularity, but right here at this inner boundary, making any prediction of what happens next completely impossible. This is where the real revolution begins. The stability of the inner horizon is a matter of intense debate. Most models suggest it is highly unstable. The mere act of someone crossing it could cause it to collapse into a true singularity or unleash an infinite wall of radiation. But let's follow the mathematics to its most radical conclusion. If a Reissner-Nordstrom black hole had a charge greater than its mass, a seemingly impossible but theoretically allowed condition, something incredible happens. Both the inner and outer event horizons would vanish. They would mathematically cancel each other out, leaving the singularity completely exposed to the rest of the universe. This is what physicists call a naked singularity. A naked singularity would be an object of infinite density just sitting in space, visible and accessible, with no event horizon to shield the outside world from its paradoxical core. This is the ultimate violation of the cosmic censorship hypothesis, first proposed by Roger Penrose. This hypothesis is not a proven law but a deeply held belief that nature abhors such paradoxes and always censors them. It always dresses a singularity with an event horizon to protect the sanctity of cause and effect throughout the rest of the cosmos. The existence of a single naked singularity would shatter this principle. The consequences would be nothing short of a revolution in physics. With direct access to a singularity, we could finally observe the precise point where general relativity and quantum mechanics collide. We could potentially test theories of quantum gravity directly, seeing how spacetime behaves under infinite curvature. It would be the ultimate cosmic laboratory, but one with terrifying implications. The complete breakdown of predictability at a naked singularity could mean that the future becomes truly random and uncalculable. The fundamental principle that every effect has a cause could simply cease to be true in its vicinity, unraveling the very logical framework upon which all of science is built. So, do they exist? Most physicists believe nature has a way of preventing this, perhaps through the instabilities we mentioned or through some undiscovered law. An object with a charge greater than its mass would fiercely repel any like charges and attract opposite ones, rapidly neutralizing itself and likely forming a horizon before it could ever become naked. The search for these objects is a search for the ultimate exception to the rules of reality. Finding one would be the most disruptive discovery in the history of science, forcing us to not just rewrite the textbooks, but to completely reinvent our understanding of predictability, causality, and the very fabric of the cosmos. But to truly push the boundaries of what a singularity might be, we must venture to a place where our very conception of reality unravels. We've explored black holes as gateways, engines, and even conscious entities, but perhaps their most profound role is as cosmic hourglasses, challenging our understanding of time itself. The singularity is not just a point where space becomes infinitely curved. It is a boundary where time as we know it may cease to exist, begin anew, or transform into something entirely unrecognizable. At the heart of every black hole lies this fundamental problem. Our two most successful theories give us completely different pictures. General relativity predicts that at the singularity, the flow of time grinds to a complete halt. Clocks would simply stop ticking. The concepts of before and after lose all meaning. It is the ultimate end of the line, not just for matter, but for causality itself. Quantum mechanics, however, with its unwavering rule that information cannot be destroyed, suggests this cannot be the final answer. It implies that time must, in some form, persist or that the singularity must be replaced by something else. A transition so profound it might redefine the beginning and end of time. This is where the quest for a theory of quantum gravity becomes essential. Our current physics treats space and time as a smooth, continuous stage upon which particles act. But many physicists believe this is an illusion, a simplification that breaks down at the smallest scales. In a theory like loop quantum gravity, space-time is not smooth. It is granular, composed of tiny, indivisible loops or pixels at the Planck scale. At this level, near a singularity, the very fabric of time might dissolve into a frothing sea of quantum possibilities. There would be no single timeline, but a superposition of potential histories, a state where cause and effect are no longer strictly defined. Time, in this view, might not flow but simply be, with our perception of its passage emerging from the decoherence of these quantum states, much like a movie emerges from the rapid progression of still frames. This radical rethinking leads to an even more staggering possibility, that the interior of a black hole could be a nursery for new universes, complete with their own arrow of time. The immense energy and curvature at the core could trigger a quantum bounce, a repulsive force so powerful that it halts the collapse and rebounds it into a new, expanding state. In this scenario, the singularity is not an end, but a bridge. The moment of infinite density becomes the Big Bang for a new space-time continuum, born within the black hole but entirely separate from our own. The time that ends for an object falling into our black hole becomes the beginning of time for a new reality within. Our universe's past, its own Big Bang, might itself be the interior of a black hole in a parent universe, suggesting a cosmic cycle of birth, death, and rebirth on a scale that dwarfs human comprehension. What, then, does this say about the nature of time before our universe began? If our cosmos was born from a black hole collapse in another reality, then the question, what was before the Big Bang? Transforms. There was no before in our timeline, but there was a elsewhere. Time existed in that parent universe, flowing in a direction that may be completely different from our own. The initial conditions of our universe, the precise settings that allowed for galaxies, stars, and life, would not be a random accident. They would be a physical inheritance, a legacy passed down from the specific physics of that parent black hole's formation. The origin of our time is thus entwined with the death of time in another cosmos. Finally, black holes may also hold clues about the ultimate fate of time in our own universe. As we look to the far, far future during the heat death, when the last black holes evaporate via Hawking radiation, what happens to time then? As space becomes ever more empty and cold, the number of measurable events, the ticks of the cosmic clock, approaches zero. In a universe devoid of change, can time truly be said to exist? The gradual evaporation of black holes might represent the final significant events, the last flickers of process and change before the cosmos settles into a timeless, equilibrium state. Black holes, therefore, bookend the story of time. Their formation might mark the fiery beginning of new temporal eras, and their slow dissolution could signal the gentle fading of time into eternity. They are not just objects in space-time, they are the keepers of time's deepest secrets, from its violent birth to its quietest end. But if harnessing a black hole's spin sounds like an engineering nightmare, another theory proposes a method so elegant it could already be happening naturally across the cosmos. No advanced technology required. This is the Blandford-Xenagic mechanism, a process that taps into a black hole's rotation not with falling objects, but with the immense power of magnetic fields. Imagine the black hole not as a simple vortex, but as the ultimate cosmic dynamo, a generator of astronomical proportions. For this process to work, the black hole must be active, surrounded by a superheated, swirling disk of material known as an accretion disk. This disk is not just gas and dust. It's a plasma, a sea of charged particles. As this turbulent material orbits at near light speed, its immense motion twists and amplifies magnetic field lines that are frozen within it, eventually weaving them into a powerful, ordered structure that threads through the black hole's ergosphere like the wires in a gigantic motor. Here's where the magic happens. The spinning black hole, dragging space-time around with it, grips these magnetic field lines and forces them to rotate. A rotating magnetic field is the fundamental principle behind any electrical generator on Earth. It induces a powerful electric current. In the extreme environment around the black hole, this process is amplified to an almost unimaginable degree. The black hole's rotation transfers its immense energy into the magnetic field, which then acts like a twisted umbilical cord, channeling that energy outward along the black hole's rotational axis. This creates two colossal jets of radiation and plasma, shooting out from the poles of the black hole at nearly the speed of light, often extending for thousands of light years into intergalactic space. We have actually observed this phenomenon. The most powerful and luminous objects in the universe, quasars and active galactic nuclei, are believed to be powered by this exact mechanism. The energy output can eclipse the combined light of every star in a galaxy, all generated by a central black hole that itself is cloaked in darkness. The Blandford-Xenagic process effectively turns the black hole into the engine of these cosmic beacons, converting the raw power of spin into a focused torrent of energy that shapes the evolution of entire galaxies. For a civilization advanced enough to replicate this, the implications are staggering. Instead of building a structure as fantastical as the Penrose process's massive mirror, they might learn to create and manipulate magnetic fields of planetary scale, directing the energy outflow into a collectible stream. This would provide a power source that is not only unimaginably vast, but also incredibly efficient and remote, posing no direct risk to the civilization harnessing it. They could, in essence, siphon the energy from a safe distance, using the black hole's own natural properties to fuel their ambitions. Together, the Penrose process and the Blandford-Xenagic mechanism transform our view of black holes from mere consumers to potential cornucopias. They are not the end of things, but could be the beginning of a new era of cosmic engineering, offering a solution to the ultimate energy crisis for any civilization that lasts long enough to master the gravity well. They represent a universe that doesn't just permit life, but in its most extreme corners, may provide the very tools needed to sustain it indefinitely. After exploring these 24 incredible ideas, we now arrive at the most radical and paradigm-shifting theory of all, a proposition that forces us to question the very existence of the objects we've been discussing. What if black holes, as classically described by Einstein's general relativity, are not real? What if they are cosmic mirages, illusions created by the stark limitations of our current physics when we try to describe nature at its most extreme? This theory doesn't just tweak the details. It suggests we have been fundamentally misinterpreting the universe's darkest landmarks, mistaking a profound failure of our equations for a physical reality. The heart of this argument lies in the unavoidable conflict at the center of a black hole, the singularity. General relativity predicts a point of infinite density where the laws of physics simply cease to function. To many physicists, an infinity in a physical theory is not a feature. It's a glaring bug, a clear sign that the theory has been pushed far beyond its limits of validity. It's the equivalent of a calculator returning an error message. It doesn't mean the answer is infinitely big, but that the calculator cannot properly handle the calculation. In this view, the prediction of a singularity is not a discovery of a real object, but a signal that we need a more complete theory, a quantum theory of gravity, to truly understand what happens when matter is compressed beyond comprehension. This has led to several proposed alternatives, objects that could mimic all the observable properties of a black hole without the problematic infinities. One of the most developed is the gravastar, short for gravitational vacuum star. Imagine an object with the immense mass of a black hole, but instead of an event horizon and a singularity, it has a thin shell of ultra-dense matter. This shell would be under tremendous pressure, but it would halt the total gravitational collapse just short of forming an event horizon. Inside this shell, the theory proposes, space would not be empty. It would be filled with a bizarre form of dark energy, a repulsive force that counteracts the inward pull of gravity and prevents the formation of a singularity. To an outside observer, a gravastar would look almost identical to a black hole. It would have incredible gravity, bend light around it, and even have a defining surface that acts as a one-way membrane for matter falling in. The key difference is that what lies within is not a void but a core of exotic energy, transforming the object from a destructive pit into a unique and stable state of matter. Another fascinating candidate is the dark energy star. This concept also replaces the central singularity with a core of the same repulsive energy that is accelerating the expansion of the universe. As matter falls onto this object, it wouldn't vanish forever. Instead, it would be converted into dark energy at the surface, a process that would release a tremendous amount of radiation. This could potentially explain some of the high-energy emissions we see from the vicinity of suspected black holes. These objects would not have true event horizons, but rather, apparent horizons that only seem to trap matter and light for a very long time, before eventually allowing energy to leak out. This offers a neat solution to the information paradox, as information wouldn't be lost behind an impenetrable barrier, but slowly radiated back into the universe. So if these alternatives exist, how could we possibly tell them apart from a classic black hole? The key will be to find a crack in the illusion, a subtle observational signature that betrays their true nature. The most promising method involves studying the very boundary that defines a black hole, the event horizon. According to general relativity, the event horizon is perfectly smooth and featureless. But the surface of a gravastar or the energy conversion layer of a dark energy star would have a physical structure, no matter how minute. When matter inevitably crashes onto this surface, it wouldn't just vanish silently. It should create a shockwave or a distinctive flash of light, a telltale sign of a hard surface that astronomers could, in theory, detect. The ultimate test may come from the next generation of gravitational wave observatories. When two black holes collide, the resulting ringdown, the way the new, larger black hole settles into its final state, produces a very specific set of gravitational wave frequencies. If the colliding objects were actually gravastars or other exotic objects with a physical surface and internal structure, their ringdown signature would be different. It would contain faint, additional frequencies, like a bell that has a slightly different ring depending on what it's made of. Detecting these extra tones in the cosmic symphony would be the smoking gun, proving that what we call a black hole is actually something else entirely. This theory, while highly speculative, is a powerful reminder that science is a process of constant questioning. Our most cherished models are not sacred texts. They are the best approximations we have until new data forces us to see the universe in a new light. The idea that black holes are illusions challenges us to be humble, to accept that the universe's greatest mysteries might not be solved by simply applying our current theories more rigorously, but by having the courage to imagine that we might have been wrong all along. It keeps the door open to a reality that is even stranger and more wonderful than we have yet been able to conceive. And so our incredible journey through the cosmic looking glass comes to a close. We've ventured from the event horizon to the singularity and beyond, exploring 25 theories that stretch the very fabric of reality. We began with the promise of wormholes, Einstein-Rosen bridges serving as tunnels through spacetime, and the mind-bending possibility that a black hole might not be an end, but a gateway to another universe or time. From there, we watched as Stephen Hawking's brilliant insight revealed that these cosmic giants are not eternal, but slowly evaporate, radiating their energy back into the void and presenting us with the profound puzzle of the information paradox. We then met the white hole, the theoretical opposite of its dark twin, violently expelling matter and energy in a cosmic outburst that might even explain our own Big Bang. We considered the astonishing idea that the elusive dark matter holding galaxies together could be a vast sea of ancient primordial black holes, remnants from the first second of creation. This led us to the holographic principle, which suggests that our entire three-dimensional reality might be a projection from a two-dimensional surface, with the event horizon acting as a cosmic hard drive, storing the information of everything that ever fell in. We dreamed of engineering marvels like the black hole starship, harnessing a micro-singularities hawking radiation for interstellar travel, and pondered whether these objects might be nature's ultimate quantum computers, or perhaps even conscious entities. We explored the radical notion that our entire universe might exist inside a black hole in a larger cosmos, and that every black hole we see might contain a new universe within itself, a fractal matryoshka doll of cosmic proportions. We untangled the twisted spacetime of rotating Kerr black holes and their ring singularities, which could potentially allow for time travel through closed time-like curves, and grappled with the firewall paradox and its potential resolution in the stringy fuzzball theory. We saw how the classic no-hair theorem is being challenged, suggesting black holes might have quantum hair that remembers their history, and how the discovery of objects in the mysterious mass gap is forcing us to reconsider the very definition of neutron stars and black holes. We examined the revolutionary idea that supermassive black holes may have formed first, acting as seeds around which galaxies coalesced, and debated whether the event horizon is a destructive firewall or a smooth, uneventful crossing as Einstein predicted. We looked trillions of years into the future to a time of infinite merging, where black holes will be the last structures in a fading cosmos. And finally, we considered the most radical proposition of all, that black holes, as we conceive them, might not even be real, but instead are illusions, gravastars, or dark energy stars in disguise. What unites these wild and wonderful ideas is not that they are all proven far from it. Their power lies in how they push the boundaries of both science and our imagination. They force us to ask deeper questions, to challenge long-held assumptions, and to remember that the universe is far stranger, more magnificent, and more interconnected than we ever dared to dream. These theories are the cutting edge of human curiosity, the place where our known physics breaks down and something new and extraordinary awaits discovery. Now we want to hear from you. After this tour of cosmic possibilities, which theory completely blew your mind? Was it the holographic universe, the black hole starship, or the idea that we might be living inside a black hole right now? Let us know your favorite in the comments below.